So it doesn't let me save until it's all done. Does that mean it's actually storing everything in RAM?
No.
No?
Well, we can check the resources it's using right now.
I have no confidence about this one.
we can check the resources it's using.
That's true. Because this doesn't look like it's actually recording into a file, because if it were recording to a file, it would have asked me about which file I'm saving it to.
It could use a system.
It could create a temp file. Yep.
Let's do a little test. Let's try to save it and see what happens before we commit.
That way we don't run
But we won't actually
Yeah.
test it for the entire period of the class. That's the issue. If you guys want to use one of your cell phones to do the recording, go ahead. Just as a backup. Okay. But we spent enough time on this one already. This is what happens when I don't have my handy dandy Linux thing up and running, which I can actually fix now, but I didn't think of it.
All of that. Oh wait,
yeah. When something doesn't work, it's a chain reaction. All right. So we'll start with something a little bit more uplifting, like your next homework assignment.
Oh, no.
I prefer the thing that I was laughing about.
Okay. Did we go over the practice test?
Oh, not enough.
We skimmed through it.
A little.
We did.
The little? Okay. So let's go back to the practice test, which is actually the quote-unquote final exam from last semester. Okay, so let's go through this and see if we have gone through everything. No, that doesn't look right. I cannot ask that question because it has structures. Reverse this one.
Could we take a peek at the first one just to see
No,
what it looks like?
this cannot be the case. Okay, that's not what we went through. Okay.
Oh, it's the actual test.
No, it's the final exam of one of the years, but it's not the one that I was looking at. All right. Okay, let's go to the right section first. I think it's this one. Okay, this is the one, final exam from 2015 fall and not spring. Okay, there we go. Yeah, that looks about right. So we did do this one, I think. It's string compare. And then this one, all the equal signs, they don't show up correctly, but we did this one as well. It is reverse engineering. So we are looking at the assembly code and we want to figure out the actual original C code. I think with this one, we did this one as well. And this is the one, implement the following subroutine. There's a recursive subroutine, and we did this one too. And this is another one. We skipped this one because we wanted to have time to talk about the last one. And the last one is the one that's separated into two subparts. The first subpart is I want you to come up with a case where it is a false positive. In other words, the code seems to be correct, even though there's a flaw in the original program. And then the second part is to come up with a case where the symptom fits a particular set of criteria. Okay, so I'm pretty sure we went through this one as well. So we did go over the entire test on Tuesday. Okay, so we're good in terms of getting through a practice test for next Tuesday. All right. Okay. So now we can work on the homework assignment, the new homework assignment. So let's go ahead and go back to course. So we'll start with a description of the homework assignment, which is actually in records and arrays. So we're actually moving forward a little bit on the records and arrays. And it is this particular homework assignment. You do have more than the usual amount of time. This one is not due next Tuesday, but the Tuesday after that. So you have like 4 or 5 days extra to work on this one. There are two reasons. One is you have to spend time to prepare for the exam. That's reason number one. And then two is you might need some time to really digest the material and I want you guys to have at least one class period to ask questions about this homework assignment. So you might want to start on it like as soon as you're done, preparing for the exam, but you might end up with questions, that you want to ask me about this one. Okay, so we'll take a quick look at the assignment itself, the description. Okay, so download this file, untar it. Your job is to implement all subroutines except for all functions defined in main.c in assembly language. Okay. So that means in order to understand the nature of this homework assignment, you really have to look into this one, and of course I'm not using Linux. Now we have a little bit of a problem. And I don't have my emulator already downloaded either, so we'll go ahead and save this one, and I will have to spend some time to download the emulator because it may be accessible as on my external drive. Let me just check it out.
Is Fox's class in session? Maybe we can ask if we can boot into the power server.
Oh right, I can do it on the power server. I manage the power server.
Oh.
So
if we
so
could-
that's definitely one of the options. But before we go there, because I hate to use the power server to run stuff for this class.
Because it sucks.
No, the power server is fine.
It's nice, but it sucks having to do that from home.
Okay,
It was
so I
nice.
do have everything here. Good. So I do have access to my external hard drive, both partitions of my external hard drive. So that is great because now I can go to Linux, go to start64.bat.
Don't we want to do 32?
Yeah.
No?
What do we want to use?
No, the 64 refers to the host operating system, not the target, not the guest. So the guest is always 32, it's just, in this case, the host is running a 64-bit version of Windows. Okay, so this will take a while because, there's no hardware acceleration when I do this in Windows. So this particular homework assignment revolves around how to deal with structures, okay, how to deal with records in C and C++, and how to translate that kind of code into assembly. So I will keep this page up because we'll go back to this one from time to time. Instead, in addition, we'll open up this slide here. How to implement C structures in assembly. Okay. So we'll start with structures, and I'm hoping that this is something that you are familiar with already. If you look at this code here, what does it do? Okay. Question number one, is this defining an actuals? Is it allocating for a variable called x, or is it defining a structure called x?
Defining a structure.
It's defining a structure. Okay, so very good. Okay. In most cases, you can look at a struct like a class, except it has everything being public. Okay. So in order to create an object or create a variable of this particular type, you use struct x as a type name, and then you specify the name of the variable. So when you combine these two, we have object1, obj1, being a structure of struct x in this case. Are we doing okay so far with this concept in C? Is that okay? All right. And let me look at the emulator. Okay, the emulator is up and running. That's good. So now we can actually do something, look at the homework assignment. So I'm going to switch gear and take a look at the homework assignment. So to transfer the file, I'm going to use WinSCP.
Does that struct have a struct inside it?
Yep, it does. And this struct has no name. The structure itself has no name, but the member has a name. So it's an anonymous structure, but it does have a name for the member.
So that
How do you reference that?
You just say c.score.
X.
So we'll get back to that one. Let me go to localhost 2200 user and live. Okay, log in. Oh, guess.
Tag is pretty good at showing us stuff that we already know in ways that we didn't know it could be used.
Which one?
The struct thing with the CI.
Oh, okay.
Never really thought about it that way.
What is it useful for?
Struct in a struct. Section. Ah.
When you don't need to define another thing of that type, then you don't need to give the structure a name. So the structure can now be anonymous.
Kind of like dynamic allocated memory, except it's not dynamic.
No, it's just that you have a member that has multiple parts because you need to access the multiple parts, but nothing else is going to be of that type, so you don't need to name the structure itself, because the whole purpose of naming a structure is you can use it as a type to stamp out other variables. But if the intention is not to use it to stamp out any other variables, the structure itself does not need another name.
As long as you're able to reference it.
It doesn't need a name. Yep. All right, so we have the file copied, and now it's just opening PuTTY to log into it. Everything takes so much longer in Windows. Yeah. There we go. We can change this font a little bit because I know this is a little bit too small. So we go to Appearance, change the font size 14, 16. Is that about right? Or is it too thin? Can you guys read that? Is that okay? Okay, so let's go ahead and start with this one. There might be a better font to use. I'm just going to tweak it a little bit. Okay. The best font to use, fixed size. Terminal is actually a good one to use. 12. Fine. Is that better? Sort of? Okay.
Yeah.
All right. So let's go ahead and untar this one first. It's tar xzvf, and then we have the file name of the tar file. So now it's undecompressed. We go to complex, which is the folder. And you don't have to do anything about main.c. This is the main.c. So when you look at main.c, it has doesn't have anything really particularly interesting. I have one function called readInt, which doesn't do a whole lot except you just read an integer int. It makes use of scanf. For those of you who don't know or have never used scanf, don't worry about this one. It will just basically keep trying until it reads an integer in base 10. That's all it does. And then in here we have several levels of call. So we read it from the inside out. We have readInt here, and then we have readInt here too. So we are reading two integers that will serve as arguments or parameters to complex init. Complex really just means a complex number, and then we read another integer and then another one to initialize another complex number. But these two complex numbers will be passed to ABC as a subroutine, which we will do some kind of processing. Let me see, did I do it right? Nope. Okay, we have one complex number from this part, we have another complex number from this part, and then we have the third one coming from this part. So ABC takes three complex numbers as parameters, and then it will do some calculations, comes back as another complex number, and then we'll go ahead and call this subroutine or function complex print to print out the value of a complex number. Is that okay? Is it complex? Okay. Well, this program is written in C, so you would expect it to run in C. So let's go ahead and make clean, and then we make the executable. This is all in C and it should run. So we say /main to run the program. You have to give it 6 integers. Okay, 1, 2, 3, 4, 5, 6, and it gives you the result, which is -8 for the real number part of the result, and the imaginary part is 40. So the C code does work. So you might want to run it in C a few times just so that you know what the program is supposed to do. Are we doing okay so far with this? Is that okay? All right? Okay. But nothing in main you have to convert into assembly. It is in the other files that you have to convert. So we have two files that you have to do the conversion. One is called complex.c, and the other one is called complextest.c. We'll take a look at complex.c first, because once we understand what we are dealing with, then we can kind of talk about those topics. This is complex init. Okay, so let's just take a look at this particular function. It takes in two integers as parameters. And do we know how to pass integers as parameters? Okay, we just push those on the stack. And because this is a 32-bit architecture, each integer is 32 bytes or takes up 4 bytes. So we kind of know that part already. It has a local variable x, which has a type of struct complex, and I'll show you the definition of struct complex a little bit later. It basically only has two members, member I for the imaginary part, and then member R for the real part. So I initialize x so that x.I is I, which is the parameter, x.R is R, and R is the parameter R, and then we just return the whole structure. Okay, because in C and C++, you can return an entire structure as the return value. Okay, but the mechanism of doing this is not going to be the same as what we have done before, because you cannot fit an entire structure into EAX in assembly. So we cannot do it that way. Okay, so this is the first problem, and we'll go ahead and see how complex is defined. It is in this particular header file, complex.h. So we'll take a look at complex.h, and this part is the actual definition of the structure. As I said, it only has two members, I and R, and they're both integers. In other words, it's not a very complex structure. It only has two members, both are integers, and that's about it. Are we doing okay so far with this code at this point? Okay, all right. So I have to illustrate all the concepts, but without using the homework as a platform to illustrate those concepts. All right. So this is what you have to do, and you do have a few subroutines to convert. I would start with one. Make sure that one is done correctly, and then move on to the next one. So you have complex init, which is the initialization of a complex structure. You can look at this as the constructor in C++. Then we have add, which is adding two complex numbers. In this case, the parameters are complex numbers. They're not pointers to structures, they are actual structures. Now, passing an entire structure to a subroutine is the same thing as passing integers or pointers to a subroutine, because you just copy the whole thing on the stack. Okay? What if the complex structure has 200 bytes? Well, then that parameter will take up 200 bytes on the stack. It's no big deal. Okay? It's basically the same technique. And the actual calculation would make use of a local variable x, so that we can calculate the imaginary part of the sum of two complex numbers, and also the real number part of a complex number. And then we have multiply down here, which is about the same thing. I will tell you guys how to do the multiply instruction, so that part will be done. And then we have the print, complex print as the last function, which is actually pretty easy. If I were to choose one to start with, I would choose this one to start with, because it doesn't change anything. It does not return a complex number. It just it has a parameter that is a complex number. It just wants to print something. So I would start with this one as the first subroutine to convert into assembly. Okay, this is one file. The other file is called complextest.c, which has a single thing to do here. It is just performing a nested call. The first call is to multiply AB, and then the product of AB is going to be a parameter or argument to complex add. So we are adding the product of AB to C, and that will be stored in X, and then we return X. Okay? Are we doing okay so far in terms of just understanding the grand scheme of things? Of the homework assignment. Not so much the mechanism of how this is done, it's just what needs to be done. Is that okay? All right. So the rest of this class is going to be an illustration of how to deal with problems like this. And I'm going to use a new folder just to illustrate that. I'll just call it struct here. And I'm going to replicate what we kind of have, but not exactly the same thing. So we'll go ahead and create the structure, and we need to find, okay, we'll just call it a, let's see, what would be good as a structure for demonstration purposes. So it illustrates the concepts, but at the same time it doesn't give away the solution, like the whole thing. Fraction is kind of the same thing. Yep, go ahead.
I was going to say something, maybe using char data types that connects the two.
Okay. Okay, I think I got the idea. We'll have a name, okay? So I'm going to define this the same way as the other one. Is that font really working out okay for you guys? Is it? Okay.
Livable.
Okay. So we have name.h, name underscore h. If not defined, define it now. And pound. And if, now all the way down here. Okay, so I'll just first explain this part, which is not really assembly language programming, but it is a very useful technique in C and C++ header file technique. The pound if and def is matched by count and if. Okay, so that's one begins the conditional compilation, the other one ends the conditional compilation. Is that part okay? Just nesting, just where is the beginning, where's the end. NDEF it means not defined. So it's basically saying count if not defined, and then name underscore h, or in uppercase, is the macro that is in question. So it's basically asking, if name underscore h is not defined as a macro, do everything in between all the way until end if. Okay, so that all of that stuff will be passed on to the compiler to be compiled. And the first thing we do is define the macro. So the idea of this is we don't want to recompile the header file multiple times, and this will avoid the actual content of a header file being compiled multiple times, even though you have pound include of the same file multiple times, because once the macro is defined, then it will skip the entire thing. Is that okay so far? Just explaining the concepts of how the pound and def works in this case. Okay. So we'll go ahead and define struct name with an uppercase N, because we follow the same convention as in C++, where the class name, a class name usually starts with an uppercase letter. And we'll just say, char last name has 256 characters, and first name has 256 characters. Okay. Now, obviously, this is bad programming practice because I use just a literal number to indicate the size or the length of each array. But it's okay because it's really just for illustration purposes. I'm not too worried, with the maintenance issue of this program. Is this part okay? Okay. All right. So we'll go ahead and save this file, and now we can move on and deal with some subroutines that can deal with that can work with a name. Okay. So we'll go ahead and edit another file. We'll go back to this file from time to time because as we add functions, we have to add it to this file. So we'll say name.c, which will implement subroutines related to name. So the first thing we have to do in the C subroutine or the C source file is to pound include name.h, so that now we know the definition of what is a struct name. And we'll just go ahead and say void name print. And with this, we have to pass a structure to it. So we'll go ahead and say struct name, and we'll pass by value. We're not passing the pointer to a structure. We're passing the entire structure by value into the subroutine. Okay, so we'll call it n. And in here, I'm just going to use printf %s, comma %s, because I'm going to print the last name first. So n dot last name. is going to be the first %s, which is the first string being printed, and dot first name is going to be the second one, because I'm printing last name first, or family name first. That's the entire subroutine. Are we still doing okay so far with this? Okay. All right. But now that I have a subroutine that is related to the structure name, I'm going to go back to the header file here and add the prototype definition into the header file. So this way, whoever is count including name.h not only gets the definition of the structure of name, but will also get all the prototypes of subroutines related to struct name. Is that okay? So far? Okay. All right. And we'll now go ahead and define the main subroutine. Oh, I forgot one thing. Name.c also now needs to count include stdio.h, because that's where printf comes from. Okay. So now we can go to main.c. Main.c needs to count include stdio, because I'm going to do something that requires standard I/O. It will also have to count include name.h, because I'm going to make use of the subroutines that I have defined earlier. And okay, so I'm going to make this one kind of fun and make use of this stuff. Okay, how many people knew that the main function of a C program actually can take on parameters? Okay, most of you already know that. Okay, good. And this is not the entire thing either. Okay, it actually has some additional parameters, but these two are the most useful ones in most cases. Argc refers to the number of arguments passed to main, which means in the shell, in the command shell, when you run main, how many additional things are you specifying? So argc, which is the count of arguments, is reflecting that. But you have to keep in mind that the executable itself counts as one of the parameters. So argv bracket 0 actually is referring to the name of the executable itself. Argv is, there are two ways to look at this. Okay, literally it is a const char pointer argv, which means argv is a pointer to a const char, which also means I'm not supposed to change those characters. The second way, which is the more helpful way to look at this, is to see argv as an array of character pointers. Okay? So let's go ahead and change the representation, because I think this is a little bit easier to read. Argv is an array of pointers to const chars. Is that okay or not? How many people understand that this is exactly the same thing as what I had earlier? Because in C and C++, a pointer is an array. Okay, very good. Okay, so I'm not going to do any error checking, so I'll just go ahead, well, maybe a little bit. If argc is greater than 2, greater than or equal to 2, then we'll go ahead and do the following, otherwise just ignore that and do nothing. Okay. And I'm just going to use string copy. So now I have to count include string.h and say string copy. Something is wrong here. What is wrong with string copy? Well, maybe the man page will tell us something about what's wrong with string copy. Man string copy. But then maybe it doesn't. Okay, it does not say anything about string copy being bad.
Same thing we were talking about earlier in the semester.
Yep.
Secure.
It's not secure. Does it say anything about it being not secure?
So warning.
Is there a warning here? I didn't see it.
The file.
Warning if there is no null byte among the first n bytes of
Okay.
SIC.
Okay. Well, we'll go ahead and just use it. I'm pretty sure we talked about why string copy is bad. because I actually had a sample program to do memory exploit, to do something the program is not supposed to do. So let's not do a string copy. Let's do a string n copy, where you have to specify the number of bytes that you're copying. But I cannot remember the arguments of string n copy, so we'll go ahead and band it again. String n copy has n being the last one. Okay, there we go. All right, so we specify the destination first. The destination is going to be the first name of my local variable. So my local variable is of type struct name, and I'll just call it var1, okay, for variable 1. So var1 dot first name is going to be the destination, and then the source, which is where it's copying from, is argv bracket 1, because argv bracket 0 is the name of the executable itself. argv1 is whatever is the first thing that is right after that. argv2 is whatever is after that one, and so on. So I'm actually accessing the parameters that I pass to the executable itself in this case. So there's no use of a standard in as the input in this program. And then I have to specify the size of var1 dot first name. That's my first string copy. And then my second one will deal with the last name. So here's the last name, and make sure this is last name as well. Okay, and argument 2, argv2. There we go. So we have to make sure it has at least 3 arguments in order for this to work. And then the next thing we want to do is just to print the name, but this time we want to print family name first. So I make a call to name print, and then pass var1 by value to get it printed. Are we still doing okay so far with this program? Is that okay? Alright. Save the file. And instead of having to compile everything individually by hand, I'm going to use the makefile. So I'm going to copy the makefile from your homework, which is complex. I'll copy over here, and then just make some tweaks so that it will work with this particular program. CSRC is reflecting the name of all the C source files. So in this case, we don't have complex whatever, but we do have a name.c. exe is the name of the executable. We'll just keep main as the name of the executable, and then there's nothing else to specify here. So when I say make, it should compile all the source files and link all the source files to the executable. And from the output of make, I think it has done everything that needs to be done. So now we'll go ahead and run the main program. But this time I'm going to specify tag as the first name, specify Aoyong as the last name, press the enter key, and this is the actual output because I did not specify a line feed. And this is the actual output, which is my family name first, comma, and then my given name. Is that okay? Does everybody understand what this program is doing? Which is not a whole lot. Is that okay? All right. Okay. So now the main challenge is how do we do name print in assembly language? In other words, in assembly language, first of all, how do we figure out name is a structure, and the first member has 256 bytes, the second member has 256 bytes, the whole thing is 512 bytes. Because we'll need all that information. So what we'll do is we'll take a look at a separate program and see if we can get some insight into that kind of information. So we'll go ahead and say define structure.c. And in this program, it is just a regular C program, nothing too tricky about this one. And it's just going to print something. I'll define a local variable, struct name var1, okay, kind of just like the other one. But what I'm interested in is where is each member of var1, okay? So I'm going to say printf, okay. I'm not going to do anything too fancy at first, but then we'll start to do something a little bit more interesting. So if I want to know where is first name compared to the beginning of the entire structure, how can I find that out? Without actually reading the struct definition itself. Okay, so conceptually, if you look at I'm going to go to my virtual whiteboard here. Alright, so in memory, when you look at a structure or an object in general, it consumes a chunk of memory. Okay? And the individual members are all just going to be using up different chunks of the overall allocation to the object. Does that make any sense? Okay. So in our specific case, we have two members. Okay. The first member is called first name. The second member is called last name. Like that, right? And as it turns out, because first name is the first member, it also has the same address as the structure itself. Is that okay so far? Okay. So my objective is to find out everything that is to know about a structure, and somehow I have to link all this information into my assembly language program. Okay. All right. But let's go back to the C code first. Okay. So we want to do something like this. I want to find out what is the difference between the address of var1.firstname and the address of var1. Just var1 itself. Okay. I just want to print the difference between these two. Okay, so let's see, do we have a problem here, and if there's a problem here, how do we fix that problem? How many people think there should not be a problem here, and how many people think there will be a problem? And you don't have to name the problem, just know that there's a problem. Is there going to be a problem here? Okay, a hint is C is considered a strongly typed programming language. So everything has a type, and the types have to match when you want to perform operations involving multiple operands or multiple arguments. So in this case, when you look at the subtraction, okay, so let's take a look at this subtraction here. What is on the left-hand side? What is the type of the thing on the left-hand side? It is the address of an array of characters, right? What about the type of the thing to the right-hand side of the subtraction? It is the address of a structure. Okay. Do they match? Nope. So C would complain about the types of the two addresses not matching, and therefore it will refuse to do the subtraction itself. Yep.
But the address is not the type of thing.
An address is not a type by itself in C or C++. An address of something is a type. So let's go ahead and do a make. Well, I guess make won't work in this case because I did not specify that in the make file. So that's the first thing you will also have to do is in the make file, you will have to add something here. So you're going to have to add struct source. Okay, you can name it any way you want to, but it's going to be something like this. And in this case, it's struct. How did I name that file? That define struct. Okay, so define struct .c is the source file, and then you will also need to name an executable for that. So struct exe is define struct itself. And then you have to make a target out of it and say, this struct exe is the result of struct source, but we replace all the .o files with we replace all the .c files with a .o file. So you have to do all of this stuff too with your own project. And then we have to append a few more items here. So struct source colon and dot C equals dot O. So that when we do a make clean, it will also remove these files. Struct source dot C equals dot D. So the dependency file and the object files will also be deleted in the process. Okay. All right. Let's go ahead and try to make this define struct executable. Now you can obviously just kind of GCC with the source name and supply the -O option to name the executable, but this way, we'll see why it is useful later on. Okay. So we save the make file, and then we say make define struct. All right, it did fail because it failed to compile. So on this line here, it says invalid operands to binary subtraction. This is the error message, which makes sense, okay, because we already knew it would complain about this. All right, if this is a problem, how do we fix this so that the subtraction would actually work and tell me the number of bytes between the beginning of first name and the beginning of the entire structure? You have to cast it. What do you want to cast it to? There are actually two options. You can cast it to a char pointer, or you can cast it to a void pointer. I was kind of surprised that it would work if you cast it to a void pointer, but apparently you can do subtraction with void pointers, if I remember correctly. Let's see if that's the case. Yep, you can actually do that. So when you run the program, it will tell you the number of bytes between the beginning of first name and the beginning of the structure itself. I remember it wrong. I thought I defined first name first, but I actually defined last name first. Are we okay with the output of this program? There are 256 bytes between the beginning of first name as a member and the beginning of the entire structure. Just to be sure, okay, just to be sure, we look back into this, the actual definition of struct name, and it is pretty clear why first name is 256 bytes away from the beginning of the entire structure. Are we doing okay so far with this stuff here? Just point to arithmetic, try to compute the number of bytes between two things. Is that okay? All right. So if that is okay, we're going to take a look at this program a little bit more and say, okay, might as well tell me the other thing too. What is the number of bytes between the beginning of last name and the beginning of the entire structure? We already know it is 0, because last name is the first member of the entire structure. So the address of last name has to be the same as the entire structure itself. And then we'll do one more thing here. And we'll ask another question. And this time I'm just asking the question of, hey, how big is a struct name? Give me the size of it in number of bytes. Well, we already know that is 512 because it has two members, each one has 256 bytes. Are we doing okay so far with all this code here? Yes? Okay. All right. So we'll go ahead and test it first, just to make sure the program does what we think it is supposed to do, because the output is 256 to represent that there are 256 between the beginning of a struct name and the member first name. The second number is 0 because it is representing that there is no bytes between the beginning of last name, the member last name, and the beginning of the entire structure, because last name is the first member of the structure. And the last one, 512, is reflecting the size of the structure itself. Since we have two members, each one has exactly 256 bytes, then we add up to 512. So are there any questions about the output of this program at this point? Yes? No? No questions? Okay. All right. So if there are no questions about this, let me do one thing here. I'll go to name.h and make some changes. So I'm going to say, oh, we don't need 256 bytes for last name. Let's change that to 128. And by the way, I also want to add something here. I'm going to add char ID. And it is a 7-digit ID, so I need to allocate 8 bytes to include the null terminator at the end. Okay, So I'm making changes to the definition of name at this point. Isn't that going to change the output of the program define struct? Well, it should, because that's what it's supposed to do. Okay. So we'll save this file, and then we go back and say, hey, make me define struct again. What do you think make should do? Because I think the make utility program is new to this class. But some people might have some exposure to the make utility program from some other classes. So I'll just kind of let you guys kind of explain that, and then I'll explain it. Does anyone?
It checks the create date times compared to the executable of the dependencies.
Exactly. So the make file, the file with the name of make file as one word, it defines the dependencies. So let's go back and take a look at that one, just so that we know what we are specifying in make file. The first chunk here, these are all really just quote unquote definition of variables. In other words, every time we see, I'll just pick one here. Every time we see CSRC in the rest of the make file, it's really the same thing as seeing name.c space main.c. In other words, they serve the same purpose as quote unquote labels in assembly language programming. It's just a symbolic name to refer to something. Is that okay? They're called variables. And then down here, we are looking at rules. This is a particular rule. A rule has at least 2 parts, but potentially 3 parts. This is the first part. This is called the target of a rule. The target of a rule specifies what are we trying to make? What are we trying to create? In this case, it is referring to $ in parentheses exe, and if you look up the definition of exe, it is main, M-A-I-N all by itself. So this is referring to the value of the variable exe, which is just main. So this rule is all about creating the executable main. Okay? Because main is the target of that rule. This is what we are trying to make. The second part, which is the part to the right-hand side of the colon, is called the dependency. This specifies what do we need in order to make main as an executable. This is the dependency. Now the dependency in this case looks kind of really long and complicated, but it's not really too bad. Let's take a look at one. The other ones will just kind of be the same thing anyway, or very similar. So if we just take a look at this one here, the $ with the open parenthesis simply means this is not really just, don't interpret CSRC literally. Okay, there's a way to compute the actual output. So this part refers to just CSRC or C source. It refers to name space main.c. Is that okay? But the second part, which is the colon, and then a .c equals .o, means, oh, by the way, replace all the extensions .c with the extension .o. In other words, it is no longer, if you look at this entire thing, it is no longer specifying the names of the source files, but is actually referring to the names of the object files corresponding to those source files. It is actually now, as a whole thing, it is now referring to name.o space main.o. Are we doing okay so far with the make file so far? Okay. Now this rule is missing the third component. The third component would be the command to actually create the target. It's missing the command because it is understood already. In other words, there's a whole bunch of hidden files associated with the make utility program. So if you just specify the name of the executable and specify a whole bunch of .o files, the make utility program already knows how to do it. So we don't have to specify the actual action to make it happen. Is that okay? All right. So that's how this works. I'm not going to spend too much time to explain the .d files. They're basically dependency files. They are really, really useful, but it's kind of out of the scope of what we want to do, and we're kind of out of time, so we don't want to spend too much time on that one. Okay. So understanding that we have rules to specify all of those things. If I just say make define struct, what the make utility program is going to look at the target, which is define struct, and say, is it up to date? Now, how does it know whether the define struct is up to date or not? It will look at the source file first, right? It will look at define struct.c and say, hey, is the timestamp of define struct.c later than the executable? Because if it is, then we have to recompile. That's pretty clear. But this time we have a pretty unique problem because we have a pound include in define struct.c, and the file that is being pound included is the one that is updated. But this is why we have the .d files. If you look at define struct.d, so let's take a look at that one. Define struct.d, which is a dependency file. It's not created yet. Okay, so if we do a make, it says it's up to date. Okay, that's because we did not specify the rules to make that .d file. There is a reason why it's not specified. Oh, there we go. Okay, so we have to add one more include here, and this time we specify that. Okay, just like pound include in a C or C++ program, a make file can use include as well, except there's no pound to the left-hand side. But what include is going to do is, in this case, is it will include whatever is specified here. And in this case, because we have struct source defined to be define struct.c, we already understand, oh, this is the wrong extension because it's a C file. So we have to change that to a C. There we go. So it is literally just including struct define struct.d, which does not even exist at this point. Okay. Is that okay? But because I forgot to include this, that's why the mechanism did not work. Okay, so we'll go ahead and say make define struct again. And this time it goes through all the compilation. This is the only one that we don't really quite understand what it's doing because it is applying two arguments, -mm and -mf, to the compiler. The other ones we should understand already. This one is generating it has a -c option, which means it's just compiling, it's not linking. The other one does not have a -c, it is just linking. But this time we do have a .d file, so we'll take a look at the .d file and see what it is. Okay, so the .d file is basically saying define struct.o, which is the object file, depends on define struct.c, which is the source file. That part is pretty obvious, right? The executable, the object file should depend on the source file. But what is mysterious is, hey, how did it figure out that name.h is also part of the dependency?
Checks the pound includes.
It checks the pound include, and that's what the GCC with the -mm and -mf did. Is it creates the dependency file. So with this dependency file, now I can make additional changes to main.h. Okay, I can now add additional stuff to it. I can say and okay, maybe just char gender. Okay, there we go. So now we change the structure again without changing name.c or define struct.c. But if I do a make again to define struct as an executable, it now understands, hey, we have to recompile the .c file. Even though the .c file, define struct.c, has not changed, but because we changed the file that the pound includes, the make utility program automatically figures out and go, oh, well, we have to recompile the object file, or recompile the source file to become the object file. But once the object file itself is updated, then we have to relink to get the new program, or the new executable. Are we doing okay so far with what the make utility program is capable of? Is that okay? All right. Okay. But if you make again, then it won't do a single thing because everything is up to date at this point. So when we run the program, define struct, now the numbers are all kind of off a little bit because of all the changes that we have made. Are we doing okay so far with this program? Okay? Now it is missing one of the items, like gender is not reflected here, nor is ID, because we didn't change the actual code in define struct. So that's why it only reflects the displacement of two members and also the overall size of the structure itself. Is that okay so far? Okay? All right. Now, we have been writing a program in C all this time. How does that have anything to do with assembly language programming? Well, I'm going to do something to this program, and you can tell me what I'm trying to do. Okay? So I'm going to go here, and instead of just printing the number, I'm going to say name, which is the name of the structure, and underscore, so I can separate the name of the member. First name equals to, just like that, and name underscore last name equals to, and then the last one is just the size of, and I'm going to use the same convention, name underscore size of equals to %d \n. Okay, and we'll just go ahead and make define struct again, and then just run it. Look at the output of this program. Does it remind you of something that we sometimes do in assembly language programming? They're kind of like label definitions, don't they? Okay, that's kind of cool. So if I go back to the main, the make file, and do something like this. Okay, so I'll specify a new rule. The new rule says, okay, I probably should use the variables just so that everything belongs in the same place, but it's not necessary. So I would say name.inc, which is, I'm just naming the file that is the target. And I say this depends on define struct. Okay? So at this point, this rule only has two parts. Name.inc is the target, which means this is the file that I want to create. Okay? It's called name.inc. And then define struct is the dependency, which means this is the file that I need in order to create name.inc. There are no built-in rules to create a file like that because it is a kind of like a special arrangement. So I'm going to have to specify the exact rule, okay, or the command to make use of define struct as an executable to create my target file, which is name.inc. Okay, so I'm going to say run define struct and redirect the output of define struct to name.inc. So I'm spelling out the actual action to make use of the dependency to create the target. So this rule is very explicit because I'm specifying all three parts. Are we doing okay so far with this particular rule? Okay. So with this, we can now go back up here and say, oh, go ahead and make me name.inc, which is the target that I just created. And it says, oh, I know exactly how to do it. I can just run define struct, redirect the output into name.inc, and we're good. Is that okay so far? Okay, all right. So that means if I go back and make changes to the header file and just say, oh, let's revert all the changes, I don't need all of this stuff here, and save the file again. And this time I'm going to say make name.inc. What do you think is going to happen? The first thing it has to do is
check the dependencies.
It will check the dependencies, and because of the checking of the dependencies, and because of the timestamp of name.h, which is in the dependency of define struct itself, what's going to happen next? It will first
Rebuild.
It will first recompile define struct.c, so we have define struct.o updated, and then we'll relink define struct.o so that we can have the executable define struct updated, and then after that it will run define struct to capture the output to become name.inc. It will do all of that stuff automatically. Yeah, you just heard me say automatically, because to many people it is magical. Not really. I know you guys want the rebuild all button.
Isn't that just make?
Yes. Make clean, then make. Yep. So that's exactly what it did. So this is a really cool mechanism. But we are still not doing any programming in assembly. What's going on here? Well, it will come, okay? Because now we want to implement the subroutine in assembly, okay? We got, what, 10 minutes? Yeah, we have enough time. Okay, so the only subroutine that we have here is name print, okay? And we want to convert it into assembly. Okay, so let's check out how to do this. Let's go ahead and do a vertical split so we can write the assembly code next to the C code. And I'll call the assembly code name.uppercase S. This time it has to be uppercase S. There we go. Because the first thing we do here is a pound include. Well, it doesn't have to be a pound include, but it's better to be a pound include. And it's going to include not the .h file because it doesn't understand a struct definition for the assembler, but it does understand the label definitions. So we're going to pound include name.inc. With a file with an extension of uppercase S, you can actually use pound include, pound if, pound endif, that sort of thing. Okay, so now we have this, and we can now say, okay, .global name print. Okay, I should really name this file as name print. Okay, uppercase S, because we want to define only one. Oh, okay, it just lost the content. We have 3 lines here. Paste. There we go. Okay. All right. So we just do the usual stuff of defining a subroutine in assembly, starting with a label definition, ending with return. And we also want to know where to find all the parameters. In this case, there's only one. So we say old EBP is 0, return address is old EBP plus 4, and then we also have the next one is going to be the parameter, which is n here. N is return address just plus 4, because this plus 4 is reflecting the size of the return address, has nothing to do with the size of n itself. Is that okay? But if I have another parameter, then the next one will depend on the size of a structure, of the structure of name. Is that okay? All right. So now we can get into the subroutine itself. The usual thing that I do is push and then followed immediately by the pop, so this way I don't forget. And then we have move ESP to EBP and move EBP back to ESP. Basically all the usual stuff, entry code, exit code, and in between, now we can implement the subroutine. In the subroutine, we have a printf, which means I have to allocate and get the string somehow. And fortunately, we do have a way to do this, so we can say format string being ASCIIs, okay, ASCIZ, which means this string is going to be null terminated, just like the C string, okay? And we'll just replicate exactly what is in the C string, which is %s, comma, %s, and then the space, and then that's the end of it. Okay. All right. The only thing we do here will be kind of two things. The first one is we have to push all the parameters, and then we call printf, and then we have to clean up the stack. How do we push parameters when we are interfacing with a C subroutine? What is the ordering?
Below.
The last parameter is pushed first.
Yep, the last parameter is pushed first because it should end up with the highest address. Okay, very good. So we have to pass the first parameter. I mean, the first thing we have to push on the stack is the address of first name of n. Okay, so now we're getting into something that's a little bit hairy, okay? Because the first thing we want to do is to take a look at the picture of the stack here. Okay, so here's the stack, and because it's passed by value, we have the entire structure on the stack. So we have the entire structure, which is a name, on the stack like this. We have the return address, which is relatively small right after that, and then we have old EBP over here. So this is old EBP, this is return address, and this is the entire parameter n, which has several parts. It has first name and last name. Are we doing okay so far with the picture of the stack? Is that okay? All right. But to use printf, we have to pass the address of the array that we are dealing with, because we're not going to pass the entire array by value. It is impossible in C or C++ to pass an array by value. Okay? So, how do we do that in assembly? Well, we have to first find the address of the parameter itself. Okay? How do we find the address of the parameter? So we can move EBP into EAX. Well, we're just using EAX for computation purposes. And then we can go ahead and add the displacement of the parameter from where EBP points to, which is in the symbol n, and we just add it to EAX. So at the end of these two instructions, EAX will become the address of the entire structure, of the entire parameter. Is that making any sense? Sort of? Because n is representing the number of bytes from where EBP points to the first byte of that parameter. So by adding these values explicitly using assembly instructions, now I have EAX pointing to the beginning of the entire structure. But that's not what I want. I want the address of a particular member. So what do I do? What about something like this? Name underscore, and we want to print, this is first name, so we say first name to EAX. Wouldn't that fix the problem? Because if EAX is already the address of the entire structure, and the label name underscore first name is the number of bytes between the beginning of the entire structure and the member first name, if I just add this, I would have the address of the member first name. Is that okay? Okay, all right. So now we just have to push it on the stack. Push EAX. What about the second parameter? This is the third parameter. The second one, hey, pretty much the same thing. So we just copy these 5 lines. Make sure that we change this to last name, and we're good. What about that format string here? You know, this literal string, %s, comma, %s. Well, we have it already defined as our format string, fmt string here. So we just push that on the stack. fmt string, and this one I can do it with one single instruction, because the label fmt string is already reflecting the address of that string. So I just need to push that on the stack. So now we have all 3 parameters on the stack. It's time to actually call printf. And after printf returns, we have to clean up the stack. Okay, even though there's nothing else, it's still good practice to clean up the stack. How many things or how many bytes do I need to clean up here? No. You have to look at the parameters that we pushed for printf. We basically just clean up after all the parameters. 12 bytes, exactly. So we say add 12 to ESP. So now it's all cleaned up. It's not 100% necessary. If you forget the add $12 to ESP, it's not going to break the program, because the next instruction will restore the stack pointer anyway. Okay? It's just that it's good practice to remember to deallocate your parameters when the subroutine call is done. Okay? All right. So this is all done, and I'm kind of confident this is going to work. So I'm going to make adjustments to the makefile again. So I would say, yes, we do have some assembly code this time. It is called name print dot uppercase S. And then the other thing we also have to do is to go back to name dot C, which is actually on the other side. And now we say, oh, by the way, do not use the C definition anymore, because otherwise we'll end up with two duplicate definitions of the label name print. Is that okay? So let's go ahead and see what happens when we say just make. Because when you say make, it's going to make the default target. The default target is really just the target of the first rule of the entire make file, which in this case is our main executable. Okay, so we say make. Wow, that actually compiled the first time. And then we can say, let's run it. Okay, that's it is supposed to complain about it because, you know, I did say that you'll check ARGC.
Is that censorship?
Oh, that's dumb. I put the actual utilization of var1 outside of the conditional statement. That was really dumb. It's kind of like ordering guardrail, you know, but not installing it. All right, so let's make again. But this is the nice thing about make is you make some changes, you just type make, press the enter key, and it will figure out what to do to bring the executable up to date. Let's go ahead and run main again, which should not do a single thing because I'm not supplying anything. Okay, that's good. So now we say, okay, let's print my name, but I want family name first, and does that correctly. Okay, I know we are running out of time, but I do want to show you one additional thing so that you can get started with the homework assignment, because otherwise we won't have time to do it on next Tuesday. So I'm going to use up the next 5 minutes for that purpose. Okay. All right. So we'll take a quick look at name.c again. And we'll say, okay, this is one subroutine that is useful, but I want another one. I want to be able to initialize a name. Now, to initialize a name, I'm going to say, let's just give me a default name. So that means the return value is going to have a type of struct name. Now, this is going to be useful because this is what you actually have to do. Okay. All right. So we'll have a default name like that. And I'm not really sure how I want to do this or not. Okay, we'll just do it like this. So that means, you know, I want to create a default name and just return it. So that means I also need a local variable struct name. We call it x, and we'll just say x first name bracket 0 is a null character, so there's no particular name. X dot last name, last name bracket 0 is also a 0. So I'm just using, you know, an empty string for both the first name and the last name, and then return x as the actual name. So I'm just doing the initialization here. And in main, just to test to see whether this code works or not, I am going to specify else. We'll do a var1 equals to name init. Is that how we call the name? Call the subroutine? Yep, name init. And then we'll go ahead and print it anyway. So this time when it prints, it should not print garbage because first name and last name should both be empty strings. So it will print a comma and a space because, you know, the names, the actual names are empty strings. Okay. All right, so this is just a test code. So we'll go back to name.c and basically say, okay, but how do we implement name init in this case? So we'll do a vertical split, and this time we'll edit name init.uppercase s. So we'll do the same trick as last time and pound include name.inc, which includes all the label definitions related to the structure of the name struct itself. And then we do the usual thing, dot global name init, return. This one is relatively easy to do because there are no parameters, so I have no, well, do we have parameters or not?
We have a local variable.
We have a local variable, but it's not 100% necessary. ESP to EBP, and then we copy EBP to ESP. Okay, kind of boring stuff here. Okay, so let's take a look at what is on the stack. Old EBP is still 0. Return address is old EBP plus 4. But if you remember from last time, we found a hidden parameter when a function is supposed to return a structure, didn't we? There's one additional parameter which is pointing to the area where you're supposed to store the return value. So we do have something in addition here. We have a return value address here, which is, in this case, our first parameter. So this is right after the return address. Okay, so this is the most important piece that you have to understand is, oh, when we return a structure from a function, there's a hidden first parameter that is a pointer to an area somewhere to store the return value. Okay? All right. So I'm going to do this the same way as in the C code. So there's no shortcut in this case. So without any shortcuts, we have to declare space for the local variable. So we have x here being old EBP minus name underscore size of. Do you guys remember how I defined the label? The size of label is really literally is the size of a struct name. Is that okay? So now we'll make use of that so that we know how many bytes to allocate for my local variable x. Okay. So in here, we just have to say, okay, let's put a 0 onto the first byte of the member first name of x. Okay. How do we do that? Well, let's take a look at the picture first. Okay. So in this case, we set up the stack a little bit differently. There's a pointer pointing to the return value. Okay, that's the first thing. That's the first parameter or hidden parameter. And then we have the return address. Okay, so this is return value, but it's really a pointer to the return value. This is the return address. And then we have the old EBP here. Old EBP. And then below old EBP is my local variable x. This is my local variable x. Like that. Is that okay? And in the variable x, we have two members, first name and last name, just like that. Is that okay? Is that picture doing okay? EBP is pointing to this point here. Okay. So I want to put a 0 here, and I want to put another 0 over there. So the question is, how many instructions do I have to go through just to do that? What do you think? So the question boils down to, if I want to access my local variable or parameters, is there an easy and quick way to do it? I'm not interested in the address of, I'm just interested in changing the content of that.
Like, since you're loading it to 0, can you just like fill the whole memory area with zeros and...
You could fill in the whole memory area, but I want to do it exactly the same way as the C code, which is only filling up 1 byte. Okay, so let's take a look at the code here. We can do it in 2 instructions. 1 instruction for each byte that we need to copy. It's a move byte, 0. Where to? Well, we know everything is relative to the EBP, so we know this is going to be a base addressing mode. We also know that this is all related to local variable x, and x is a label defined to become the displacement from where EBP points to the first byte of the local variable. So this is a good starting point, okay? Because we know, how to get to the local variable. But we don't need to access the entire variable, we just need a part of it, okay? Which part? Well, according to the C code, we want to initialize the first name first, okay? So we use the label name underscore first name, which is defined to be the number of bytes between the member first name and the beginning of the structure. We just add it. But hold on a second here. We also have the indexing operator here. We only want to change the first byte. Fine. Specify that. That's it. Because we are not computing the address. When you're not computing the address, it's actually pretty easy to get to any part of a local variable or a parameter that is a structure. Okay, the last name is just like that. So that will finish up pretty much the 2 assignment operations in the C code. The only thing left now is to return X. Okay, remember X is a local variable. It goes away by the time we get to move L, EBP to ESP, because then we're deallocating everything that is local to this location in the subroutine itself. So we can't really do anything relying on local variable X, except we can copy that around. Okay? So what we want to do is to copy X to where return value points to. That's what we want to do. But there's a whole bunch of bytes to copy. I don't want to spend my time typing hundreds of move bytes. So what do? We can use a loop, but there's something even better. That something better is called memcopy. So let's do a memcopy, because I cannot remember the ordering of the parameters. Okay, so memcopy says you are copying n bytes, which is the last parameter, from source to destination. In other words, it's almost exactly like string copy with one minor difference. It doesn't stop when it hits the null byte. String copy does. Memcopy keeps on going. If you ask it to copy 200 bytes, it will copy 200 bytes, including all the null bytes. Is that okay? But since it's a function call, it's easy to set up, instead of running my own loop to copy hundreds of bytes, I'm just going to call this subroutine. So we have to push n, and then source, and then destination. Okay, there we go. All right, so we just have to do exactly that. We push the number of bytes to copy. Do we have a label that is useful to indicate the number of bytes to copy? It's already on this screen somewhere. Name underscore size of. Thank you. Name underscore size of. That is the number of bytes that we have to copy. Now we have to specify the source. Okay, where are we copying from? We're copying from X, but we cannot just say X %EBP. That won't work, because this is specifying the content of the structure, not the address of the structure. So this is not going to work. Ideally speaking, we just want to say ampersand the whole thing, but that doesn't work in assembly language. So what we're going to do is we say push EBP first, okay, which is close to where we want, but not quite exactly. Then we say let's adjust it, let's tweak that, okay. So we'll tweak it by the displacement to X itself, which is label X, and also we want to specify, oh no, X is all that we need. So we'll make adjustment to what we just pushed on the stack, which is in parentheses ESP. So I pushed EBP first, which is close to what I want, and then I make adjustments to what I just pushed on the stack. Is that okay? Okay. So that's the address of the source where I'm copying from. Now I have to specify where am I copying to. Okay, so where am I copying to? I mean, if you just read my comment here, what does it say? Copy X to where return address points to, okay? But this time I can just say return value EBP, because that is already specifying an address. Because return the 4 bytes at return value, the label, is actually the address of where I'm supposed to store the return value. So I just need to push that address on the stack. But don't forget to install the guardrail, which is to call memset, and then we deallocate the 12 bytes that we have just pushed on the stack by adding 12 to ESP. That will accomplish the return X here. Okay? Are we sort of doing okay? Okay. All right. So now here comes the moment of truth. Well, almost. We have to adjust the makefile again. So this time we say, oh, by the way, there's one more file specified in assembly source code. It's name, what is it? init.uppercase-s. So we just have to add that one. And then go back to the C source file and comment out the C source file for that function. And now we can say, let's go ahead and give it a try. Okay, it does complain. Implicit declaration. Oh, okay, that's my bad, because I did not add it to the .h file. So main.c doesn't know what to do with name init. So we say struct name init no parameters. Make again. All right. So let's check out the program with no parameters. Oh, that is. It went all the way up to the beginning of the screen, which is probably not the right thing to do. That is certainly not the right thing to do. Okay, so it's not working. Well, technically we have until 9:50.
No.
Yes. Okay, let's. Okay, I'll give myself. How about another 5 minutes? I'm using time that is actually allocated to the task, so.
I think there's some Stack Overflow happening.
Timeout. Okay, so I'm opening up both files at the same time, and we just need to find out, okay, what is wrong about this code. It didn't crash, which means, things are still happening, but it's not being copied correctly. Okay, so we'll take a look at this one first. Okay. Oh, I forgot one stupid thing. Once again, I ordered the guardrail. I had, the road already drilled to install the guardrail, but I forgot to install. I got everything ready, except I did not install. In this case, where is X? Well, we know where X is supposed to be, but is that space allocated? Nope. Then how do I allocate space for X? I forgot this little thing here to allocate space on the stack for my local variable. So this is what happens if you don't do that. Okay? And trust me, it was not intentional.
Nobody likes to.
Yeah, but at least I spot this problem, or at least one of the problems is this one. So we say make again, do a run, and it's still doing that.
You in the add long you reference cisp, is that correct? So instead of adding x to the memory address, you add it to the value it's pointing to.
Okay.
Is that
Okay, this is mems. Oh, the other problem I cannot spell. I meant memcopy, not memset. Memset is filling up memory with a particular byte pattern, which probably explains why we get all that gibberish, but it's uniform, okay? But we need actually memcopy. Okay. Yay, that works. So two problems. One, I forgot to allocate for the local variable. Two, I called the wrong subroutine. Now, there's really no saving from that one. If I call the wrong subroutine, obviously it's not going to do what it's supposed to. Okay, so hopefully this is all getting recorded, including the voice portion. So I'm going to save all the files and then put them together and then upload it later on. The lecture ends here, so I know I'm running over by 20 minutes. So I'm going to ask Derek for a raise because of that, like a bonus or something. And the best thing is it's all getting recorded. I got proof that I actually worked overtime. If you want to work on this homework assignment now, at least a little bit, I'll be over at the lab once I save all the files and so that I can do all the processing later on.
I gotta